Okay, everybody, can you, if my audio is good? My laptop is acting weird this morning, right after meeting. But how was your weekend? Oh, it's the entire Teams. I thought it was just my laptop when I plugged in my microphone. Well, something's funny is going on. Oh, good. Yeah, I had a busy weekend. I'm finishing writing my dissertation. But anyway, so I hope your weekend was still good after seeing the result of test two. So I made a poll in the lab meeting channel. I just want to know what was just to have a feeling or an idea of how you are doing in the class. By the way, I guess you have until Friday to email me if you have some questions on how the exam was graded. So again, I might not be the one who graded your exam. So if you have questions on how it was graded or you feel that add more points on a particular item, just let me know. Send me an email or a chat via Teams, and then I'll take a look at it. Kindly attach the PDF file of your grade of your test with the same file name, so I can cross reference it with the files on our server. But yeah, kindly do that by Friday so that we can decide to give you or not. Okay. So for today, we'll continue talking about section 8. And I warned you last week that section 8, yes, at least for me, it's tougher than other chapters or sections. Here we talk about different integration techniques, and these integration techniques are quite related to each other in the sense that if you apply one of these techniques, you might need to use another technique. And another complication might be in the tests or in the quizzes, you will not be told exactly what to apply. So you need to develop this kind of intuition or instinct on choosing what would be the most probable technique to be used in a particular problem or what would be the most convenient one. There are some problems that can be solvable by one technique. So you need to distinguish which one is more convenient for you. Others, there's only one that suits them. Okay. Of course, but in any case, you try use substitution first because that's the easiest to do. For today, we'll talk about trigonometric substitution, which is basically a technique in integration we use whenever we are dealing with some square. We'll see later that though we seem to be making the problem more complicated because you might be given a purely algebraic integrand, and then what we'll do is to transform that into an integral that will involve trigonometric functions. And the reason why we want to do that is to get rid of the square root. So because here we'll consider, I guess, three cases. So here are the general cases under this topic. Okay. So you can have square root of a squared minus x squared, square root of a squared plus x squared, or the square root of x squared minus a squared. Again, one difficulty with evaluating these integrals would be the square roots. Of course, you will try use substitution first because there might be some other factors in the integrand that you can use in order to get the appropriate choice for du, and that should be your first choice of method before going to trigonometric substitution. So worksheet number 10, I guess some of these problems are solvable by simple use substitution. Of course, you can still solve them by trigonometric substitution, but your solution would be right. So problem number 1 is solvable by your usual integral involving arc sine. Problem number 2 can by using the use substitution u equals x squared, because there you need du equals 2x dx, which can easily be down from the numerator. So there's no I guess there's a reason why you will try trigonometric substitution. So that's one lesson there. Try direct use substitution first before doing trig sub, right? But if all of those cases, if all those easy techniques work, for instance, for problem number 3, right? You have x squared over root of 9 minus x squared. You can try letting u to be equal to 9 minus x squared. That will require du equals 2x, negative 2x dx. But you have an x in the numerator, but after doing the u substitution, you will have a leftover top, and that will still be a radical, right? And integrating radical is not a good, it's not an easy thing to do, right? So here for problem number 3, at least, as a cursory check, I don't think it's easy to find to use that in cases by substitution. So for trigonometric substitution, if you see an integral this, or if you see a radicand, or sorry, if you see an integrand that has this radical, well, here the suggestion is to let x to be equal to a sine theta. So that's why it's called trigonometric substitution, because here we are turning to trigonometric function. So the variable x will be replaced by the trigonometric function a sine theta. Okay. Now, if you do this, then of course you will need to change the differential, but that's easy. You take the derivative of both sides with respect to theta. So a cosine theta d theta. And again, at first sight, this might look like complicating the integral, right? But if you apply a trigonometric identity into the substitution or into the integral, then we can get rid of the radical, which was the cause of the difficulty here. So if we do the substitution, then the square root of a squared minus x squared will be turned into a squared minus a squared sine squared theta. Okay, and the good thing about this, you can factor a squared out and have 1 minus sine squared theta, right? And then note that 1 minus sine squared theta by the Pythagorean identity is a squared cosine squared theta. And now we can get rid of the radical by putting cosine theta in absolute value bars, right? I guess this is one concept, the absolute value bars when you take the square root of that trig function. But the good thing here is that we can rid of the radicals, right? Now, if you are an indefinite, we can just assume that cosine theta is positive. So that means this guy could be written as the absolute value of a times cosine theta. Right? So that's the usual convention. Get rid of the absolute value bars. So once you take the square root, we take the positive root as a matter of convention for indefinite integrals. But whenever dealing with the integrals, I mean, when your integral has bounds for x's, then worry about whether we simply drop the absolute value bars or should we put a negative sign in front of whatever is inside the absolute value bars. Maybe I'll show you an example of that if we have time towards the end. But I browsed through the textbook and they just considered also in your lecture notes easy cases, right? But I'll show you one complication later. But that's our assumption for indefinite integrals. You can just drop the absolute value bars for the trigonometric functions, right? But again, for definite integrals, that's another thing. We need to consider the bounds of integration. So we see that for this first case, the motivating identity is a Pythagorean identity. We let x be equal to a sine theta so that we can apply the identity for 1 minus sine squared being a sine squared theta. Okay. Now, for the other two here, if you have a squared plus x squared, you can let x be equal to a tangent theta. identity here is that 1 squared theta is equal to secant squared theta. So maybe I should write that down here so that when you review these notes, you have something to look at. So here, identity is 1 plus tangent squared theta equals secant squared theta, right? So, and then for the last one, for x squared minus a squared, we let x to be equal to a secant theta. And the motivating identity is secant squared theta minus 1 equals tangent squared theta. So basically, if you hate memorization, this is not that hard to remember, because you just need to recall the trigonometries and look at what form can be used for these three integrals. Of course, instead of these three functions, you can use the corresponding partners of the trig functions insofar as these identities are concerned. For instance, for bullet number 1, here you could have chosen to let u to be equal to let x be equal to a cosine theta. That's perfectly fine. You'll use the cosine squared theta equals sine squared. Here you could have chosen a cotangent theta. There's nothing wrong. You just need to adjust the identity that you'll use. And for this one, you could have chosen to use a. But I guess these are the common choices that we do. I see a couple of questions in the chat, so I'll go over them. Yes, let's see. The first two questions was about the topic, but I think then something about the powers of trig functions. Haven't we considered the similar from last Friday with this? Let me see. Yeah, I'll go there first before proceeding with examples. Let's see. That's worksheet 9. Let me see. Yeah, I guess we did something similar to that problem last meeting. And I guess this is my last example last week. I'm able to, but here I uploaded the complete solution to the in my website, so you can take a look at it. Because I guess I stopped somewhere here last time and asked you to continue the solution. So though it's very similar to your problem. The given here is tangent to the fifth 9x. In your actual quiz, it was 3 tangent to the fifth 2x. Well, I guess you can follow the solution sheet. Is that okay? So solution, you split the tangent to the fifth into tangent cubed times tangent squared. And the secant identity for tangent squared, and come up with this form. But here, the first term can easily be evaluated by a simple u substitution. You can let u to be equal to your tangent, which will require a secant squared as your du. So you can evaluate it. Here would be evaluating tangent cubed. And for evaluating tangent cubed, you need to repeat the same process we did before, right? So you have tangent cubed now, before you have tangent to the fifth. But my strategy here is to isolate that there, leave 9x there, use the secant squared identity for tangent squared, and then multiply them together. And I'm always doing that because I am anticipating that I will x. And if I let u to be equal to tangent 9x, I will need a secant squared as my du. Okay. And you see that if you do this process iteratively, then you're 2 power less than what you started, right? So when we get to the fifth in the to the third after my first solution, and then after evaluating tangent cubed, now reduced to tangent to the integral of tangent, And at that point, I will use a formula for the integral of tangent. Remember that the integral of tangent would be ln of secant. Okay. So yeah, this part of the worksheet is available in my website in the updated. I finished it last time. I didn't have the time, but I completed it in the sheet. So you can follow these steps in solving your problem, Muriel. And I hope somebody liked. I also saw that somebody liked the questions. Some of you might have some problems with this. I included a detailed solution on the web, and take a look at it. And if you have some questions, just let me know. Okay. Am I still cutting off? My audio is not that good. Yeah, my Teams is yeah, a bit glitchy. But let me know if the problem persists. I hope it's bearable, because otherwise I'll need to try to restart. Yeah, I don't know what's happening. I guess partly it's with my laptop. Whenever I plug some audio equipment or use some Bluetooth with it, it kind of interferes with how Teams work. I don't know what's the problem. I keep updating my laptop, all my drivers, almost to make sure I have the latest drivers, but I still have the problem. But I hope it's bearable, so I don't to restart because we will lose a couple of minutes for that. Hey, yeah, just let me know when it starts to be non-bearable, so I can try to how we can remedy it. But hopefully, hopefully you'll understand the gist of what I'm saying. Okay, again, just call my attention if the problem persists and you cannot bear it anymore. Okay, let's try with some easy problems. Problem number 3. Easy ones, or go to the interesting ones right ahead. So because I saw your lecture notes, and it looks like you had a lot of examples for this. Yeah, I'll start with an easy example first, just to recall the. And then let's just up the level of difficulty later when we go to the next couple of examples. One is this: x squared over root of 9 minus x squared. Again, a simple u substitution. So I'll go to my next resort, which is to use trigonometric substitution, right? So if I look at the integral, if I look at the radical, or in particular the radicand, it begs me to use the Pythagorean identity with the sine minus sine cosine squared, right? So that's what I'm going to do here. I will let x be equal to 3 sine theta. Remember here that a is equal to 3 because you have a 9 here. So that's 3 squared. So I'll choose my substitution for x to be 3 sine theta. But I can that 9 will be only, okay? So that's how I got that constant in front. And then remember that whenever changing the variables, we also change the differential. So you need to solve for dx. What should replace dx? So if you replace dx, or if you compute for dx, then we'll get 3 cosine theta, d theta, right? And again, the deal here is when you change one of those, we should change all of the expressions, right? So if we do the substitution, then the denominator would be 9 minus 9 sine squared theta. Okay, and then dx will be replaced by 3 cosine theta d theta. But here we still have an x squared on top. Also need to change it into the variable theta. For substitution statement here, you compute for x squared by squaring both sides. So we get this one, right? 9 squared theta. So now all of my variables are now in theta. So I can start now trying to try to evaluate this. Okay. Now I can put the constants out. Then I'll have a sine squared theta cosine top. And here I'll have, well, I can factor it as 9 times 1 minus sine squared theta. And that's the reason I chose to be equal to 3 sine theta. So I can factor the 9 out. So I'll have a 1 minus the square of the trig identity. So here we'll have 27 integral of sine squared theta cosine squared theta all over 3. And then 1 minus sine squared, we mentioned that that's going to be cosine squared theta, d theta. All right, and then I took out 9 out of the radical, so I got 3. And then we'll get 9 outside, so that's 3. And then sine squared theta, cosine squared theta, all over. Oh yeah, thank you, Muriel. Sorry about that. That is just a cosine theta. Okay. Cosine theta d theta. And I think that's fine. Okay. And then here I can cancel. Oops, there should be no 3 anymore. I already took that. And then I'll cancel cosine there. So we'll have 9 integral of sine squared theta d theta. Okay, and now this is what I'm saying earlier, that these methods can be linked with the other techniques in the chapter. So for instance, here, after doing all the manipulations, we came up with the integral of sine squared theta, and it's a power of trig function. So you need to go back to section 8, how it is evaluated. So this often comes up because here we're dealing with trig functions, and it is very likely that we'll end up with some trig functions, right? Do you remember what we did with the with even powers of sine? Okay, just cut out for a moment there. But for the integral of sine squared theta, we need to use the half angle identity. So here we'll have 9 times minus cosine 2 theta all over 2. This is still inside the integral. I think my my hands is still on weekend mode, so it's writing something else. So okay, I guess that's it. Yeah, Herson, you're correct. We use that half angle identity. Okay, hello guys. Can you hear me now?
Yes, we can.
Okay, yeah, sorry about that. I'll just leave from my laptop and I'll use my iPad alone. So okay, so let me go back. All right. So okay, so any questions about this step? Is it good? All right, so if there are no questions, then the next thing to do is to revert to the original variable, right? Remember here that our original variable was in terms of x. Now, what I have here is an integral in terms of the variable theta, right? So here, I need to go back and use my substitution statement. Remember, we let x to be equal to 3 sine theta, okay? So that means x over 3 is equal to sine theta, right? I have a theta there, so I can say that theta, I can choose theta by convention to be the arc sine of x over 3, okay? By solving for theta from both sides. So if you have a theta, then this is a usual choice for the new variable. We choose the arc sine of whatever is the other side to sine theta. Okay. And actually, you can also use this theta and replace the theta you see here by arc sine of x over 3. So you'll have sine of 2 times arc sine of x over 3. But that doesn't look too elegant, or that doesn't look to be simple enough, especially if you are solving for a definite integral. So the suggestion is used for discrete functions. We usually use what do you call this? We use a triangle to find the value of theta, right? So here, or to find the value of the trig functions for theta. So here, let's say theta is over here, okay? And then, of course, here, look at this statement here. We say that sine theta is equal to x over 3. Remember, sine is opposite over hypotenuse from your SOHCAHTOA. So that tells us that the hypotenuse of of the triangle on which this sine theta was derived has length 3. Okay, because it goes in the denominator. And then opposite theta should be x units. So if I drew theta to be here, then opposite it should be x units, right? And then by Pythagorean identity, the third side would be 9 minus x squared, right? Now, but unfortunately here, I cannot use this directly because here we have sine 2 theta to replace and not just sine theta. So what I need to do there is to apply another trigonometric identity. So here remember that sine 2 theta is equal to 2 sine theta cosine theta, right? And now here we'll have 2. We know that sine theta is x over 3 from our substitution statement. But what is cosine theta? Remember, cosine theta is what? Adjacent over hypotenuse from your SOHCAHTOA from high school, right? So if this is our theta, adjacent to it is this guy. So it's going to be root of 9 minus x squared all over the hypotenuse, but the hypotenuse is just 3, right? So that means this would be cosine theta. So we'll have 9 minus x squared over 3 here. And that tells us that sine 2 theta is 2x root of 9 minus x squared all over 9. Just make it a little bit smaller, a little bit here. Okay. So finally, we have the integral. Let us just rewrite it here. X squared root of 9 minus x squared dx is equal to 9 halves and then theta, but we know theta is arc sine of x over 3
minus sine 2 theta, but sine 2 theta is 2x root of 9 minus x squared all over 9. Then there's an over 2 from there, plus the arbitrary constant c. Let's just simplify it a bit. We'll have 9 halves arc sine of x over 3 minus, so I can cancel the 2's. And then I can cancel the 9 outside. So I'll have minus x root of 9 minus x squared all over 2 plus the arbitrary constant c. All right. Any questions with that? Let me just go back a bit and see if you have questions. This is my problem now. I'm just working with a single screen. All right. Is that clear? Okay, so I thought that should be I thought that would be quicker because I started with a very simple example. But I hope you get the process. So now let's go to some of the questions that was sent via the chat. Let me go here and see. Even the internet here at the campus is a bit glitchy also. So, okay. Yeah, I think this one from Michael is good. Take a screenshot and then go here. All right. So here, I guess this is a similar, but we will use a different motivating identity for this. Again, you try u substitution first and see if that will work. But for that, I will let u to be equal to, my candidate is x squared plus 7. But if I do so, du will be equal to 2x dx, which I cannot, which I can get from the top, but that will have an x remaining, and that will still have a square root in it. So I won't use that substitution. So here I'll go for the for the trigonometric substitution. So for this, I will let x to be equal to, look at the form, it's x squared plus a squared. So for that, I will use the arctangent, the tangent identity. Finally, my laptop is on again. Okay. Yeah, I see Maria. Okay, yeah, Maria, you can choose that. You can use that identity. That's fine. That's exactly what I used. Right. So for the integral of sine squared theta. So that would be this. That will give you the same answer. So though, if you're good at memorization, then that's fine. You can memorize that formula. Otherwise, you'll need to do the long solution that I did before. But I guess if Dr. Almus presented that in the lecture, then you can just put that also in your list of integrals to memorize, and then you can use this in the exam without doing the half angle identity that I have shown. Okay, going back to this problem. So I guess the motivating identity here is the tangent function. So I will let x to be equal to 7, tangent theta, right? But again, that will require also change in the differential. So dx will be 7 secant squared theta d theta, okay? And then now let's go to the integral. And we need to replace everything by by the variable theta. So here, this will become 5 times 49 tangent squared theta, right? That's our substitute for x squared. All over, this would be 7 tangent squared theta plus 7 raised to the 3 halves times 7 secant squared theta d theta. All right. So just putting all those all the functions involved in the original integrand in terms of the variable theta. Then let's start simplifying this trig expression over here. So here we'll have I'll just keep the 5 times 7 times 49 on top. I won't carry out the multiplication yet. I'll be hoping that some of them will cancel each other out, right? And then in the denominator, so we have a 7 and then times a tangent squared theta plus 1 after factoring out that 7. So I'll have a 3 halves there and then still a d theta. And then we'll have 5 times 7 times 49 tangent squared theta, secant squared theta still on top. And then I'll have a 7 to the 3 halves there. And then the tangent squared theta plus 1 can be replaced by secant squared theta to the 3 halves d theta. Okay. And then here, I can have, I can cancel some of the 7s here. So this is 7 to the 7 to the 1. Here you have 7 to the 3 halves. When we do the division, that's 1 minus 3 halves. So I'll have square root left in the denominator. So I'll have 5 times 49 over root of 7. And then I'll have tangent squared theta, secant squared theta, all over secant cube theta d theta. Okay? And then we can further simplify. I'll take the constants out. So this is 5 times 49, root 7. And then we'll have integral of tangent squared theta over secant theta d theta. All right. Can somebody use a calculator for 5 times 49? I hate doing arithmetic, but that actually is half of 490. So that's 245, I think. Is that correct? Yeah, just kindly check this 245 over root 7. And then I need to integrate this tangent squared over secant theta. I guess here I can use trigonometric identities. Let's see. Yeah, I can write it as tangent squared is secant squared theta minus 1 all over secant theta d theta. Okay. And then here I can perform the division. So I'll have a secant theta minus 1 over secant, but 1 over secant is cosine theta d theta. Okay. So you see here, I'm playing with identities in order to evaluate the resulting trigonometric expression, trigonometric integral there. There might be some other techniques that you can employ, but I guess this is the easiest one, at least from the methods that I'm thinking on top of my head. So yeah, and then perform the division. Okay, are you guys still with me? Now, the good thing about this form I have right now is I can integrate them term by term, right? So integral of secant theta is ln of the absolute value of secant theta plus tangent theta. Then integral of negative cosine is negative sine theta plus the arbitrary constant c. Now we're done integrating, so the next step would be to revert to the original variable, all right? So recall that we let x to be equal to 7 tangent theta. So that means tangent theta is x over 7. But remember, tangent from your SOHCAHTOA is opposite over adjacent. So you draw a triangle, okay? Pick where to put theta. Of course, you cannot put theta here because that's the right angle there, but you can choose it to be here or over here. I'll just put theta over here, but it doesn't matter if you put it on top. Just be careful putting the variables here. So, okay, so opposite theta should be x. So theta is here. Opposite to it should be x. Okay. And then let me put theta a little bit closer here. Okay. And then adjacent to theta should be 7 units. So here is theta. Adjacent to it should be 7 units. And the hypotenuse can be computed using the Pythagorean identity, right? It's going to be x squared plus, or actually I did a mistake early on. This should be x squared plus, I want x squared plus 7, so this should be root of 7. Sorry about that. Let me go here. Yeah. I forgot that this 7 stands for a squared. Okay. So that means a squared is 7, so we should choose a to be root 7. So this should be root 7. This should be root 7. Where else? So this should be root 7. This is root of 7. And then we have here root of 7. So there would be a whole 7 left here. And then 7 there. And then we'll have just 35. Yeah, I hope that corrects the solution. Let me just take another look. Yeah, I overlooked that. Remember that 7 stands for a squared, so we should have picked x to be equal to root of 7 tangent theta. So if that's the case, then dx was changed over here. I guess that's fine. Okay, change that here. And then that's fine. I have a 7. 7 will come up with an exponent 3/2. We have a root 7 here. When we divide them, there would be a 7 left in the denominator. And then I'll cancel it with the 7 from the 49. So I'll have 5 times 7, 35. And then we got this. Okay. Do you think I fixed the problem now with that constant 7? Why did I notice that something must be wrong? Right. Because when you do the triangle, then one of these 3 quantities should be one from the original problem, right? If you go back to the original problem, it has an x plus 7 to the 3/2. So there should be a square root of x squared plus 7 somewhere in my triangle. If x was 7 tangent theta, then I would have an x squared plus 49. So that's where I sense something is wrong, because I should get a radical that looks like the one from the original problem. All right. So that's how I traced there's something wrong with the solution. So let me correct this a bit further. This should be 35. This should be 35. Okay. And then now let's continue our solution. So this would be 35 ln of the absolute value of secant. Secant is the reciprocal of cosine, so that should be hypotenuse over adjacent, so over root 7, right? So maybe I should write that down here. Secant theta is hypotenuse over adjacent, and sine is opposite over hypotenuse, right? So those are the things I need over here. So secant being hypotenuse over adjacent would be root of x squared plus 7 all over root of 7. Right? That's how I got this. Plus tangent theta. Tangent theta we knew is x over root 7 minus sine theta. So sine theta is opposite, so that's x over the hypotenuse x squared plus 7 plus the arbitrary constant c. All right. Any questions so far? I guess the solutions are just lengthy, and you need to be careful with dealing with the trig functions that will come out of the simplification. Yeah, it's Arsalan is quite hard at the beginning, but I believe that with some practice, then this should come out easy. But of course, it will natural. It won't come right away, so you need to practice a bit. Um, yeah, let me try the other question sent via the chat. So the question was the integral of 3 over e to the x root of 10 plus e to the 2x dx, right? So here you still have a radical, but the thing is that we have extra exponential functions involved. So there are several ways on how to do it. I prefer, yeah, we can take a look at the radical. So maybe I'll show you the solution this way. I can think of two ways how to solve this problem, but I guess this is simpler. So remember here, our target is the tangent identity, right? Because there is a 10 plus something squared in the in the radical, right? So I want e to the 2x to be equal to 10 tangent squared theta. So that's our target, right? So that when I replace e to the 2x by 10 tangent squared theta, first thing I can do is to factor 10 out and be left with 1 plus tangent squared theta, which is very fine with us because we can replace it by secant squared theta, right? So this is how I derive the right substitution over here. And to get the substitution, then I can get e to the x, take the square root of both sides. So I'll have e to the x equals root 10 tangent theta. So that would be my substitution. I will let e to the x, or I will replace e to the x by root of 10 tangent theta. Okay, so I will do this substitution, and then I need to compute the derivative, right? To find the substitute for dx. But to do that, we need to take the differential of both sides, right? If I take the differential of this becomes the differential of e to the x equals the differential of root 10 tangent theta. Okay, we take the differential. So the differential of e to the x is e to the x dx equals, here we have root 10 secant squared theta d theta. Okay, now I guess we are now prepared to do this. Let me see. Oh, and actually we are not yet prepared for that, because you see here, in order to get the root 10 secant squared theta d theta, I need to have an e to the x dx, right? So that means I have a little bit of a problem here, but I can remedy that by writing this original expression as e to the x dx, and then e to the x root of 10 plus e to the 2x, right? And they agree that this is the same as the original problem, because I can simply cancel these two guys out, and then I'm back at the original expression. It's just that I need an e to the x dx to be on the numerator in order to get that d theta, right? Okay, so if that's the case, then I can have it as 3, or the integral of 3. E to the x dx will be replaced by root 10 secant squared theta d theta all over. Now I have e to the x times e to the x, that's e to the 2x. But we said that e to the 2x will be replaced by this guy, 10 tangent squared theta. And then we'll have root of 10 plus 10 tangent squared theta. And now just looking at this this current form, some students will give up and see and think that this is too much to evaluate. But let's see if we can simplify it a bit. So, okay. So here I'll have I can work with these two guys out. So there would be what? There would be a root 10 in the denominator. So I'll have 3 over root 10 out of the integral. And then I'll have a secant squared theta, d theta, all over tangent squared theta. And then I can have a root of 10 times 1 plus tangent squared theta, which is the form that we wanted, why we performed the trigonometric substitution. Then we'll have secant squared theta d theta all over root 10 secant theta tangent squared theta. And then we'll have 3/10 integral of secant theta d theta all over tangent squared theta. All right. And what can we do with this form? Well, let me try this and play with identities. Let me see if this will work. I can write secant as 1 over cosine. And then I'll have a tangent squared, but that is sine squared theta over cosine squared theta. And the thing is, I can cancel one of the cosines. So I'll have 3/10 d theta over sine squared theta. And then there would be a cosine theta on top. Yeah, Harrison, that's also fine. That's the other method that I was thinking earlier. Yeah, you could have did a u sub where u equals e to the x, but yeah, but you will still end up with the same trigonometric integral over here because you will have a 9 plus u squared. Okay, so it's just you will start with a u sub, and I did the u sub integrated into the trigonometric substitution. So because I anticipate another u sub here at the bottom, so I will let u to be equal to sine theta. So du will be cosine theta d theta. So that's going to be 3/10 integral of du over u squared. Okay, so that's 3/10 of what? U to the -1 over -1 plus the arbitrary constant c. So this would be -3/10 of 1 over sine theta plus c. Okay. And then now we need to go back to the original variable x. We'll just remember what our substitution was. Our substitution was this. E to the x equals root 10 tangent theta. So that means tangent theta is equal to e to the x over root 10. And this is opposite over adjacent. So if theta here is here, opposite it would be e to the x. Adjacent to it will be root 10. And so the hypotenuse is 10 plus e to the 2x, which is what we got in the original integral. And then so let me just copy the original integral here, just so that I have a complete sentence to conclude the solution. Okay, paste. Equals, let's see. We know it's -3/10 of 1 over sine. Looking at the figure, sine theta is opposite over hypotenuse, right? So that would be e to the x over root of 10 plus e to the 2x plus the arbitrary constant c, and then we can rewrite it as -3 root of 10 plus e to the 2x all over 10 e to the x plus c. That was another long one. But at least hopefully, I hope that you understand the process. And I agree that this is quite, this could be hard because, for one, this is a long solution. It involves several steps. But so that means you really need to do some practice. So it's a good thing that we answered 4 problems today in the lab together, and we just spent one of the problems from the exercises. So try to answer the rest of these problems from the worksheet. Again, these are lifted from the textbook, so if you can access the textbook, you will get the answers to the odd numbered exercises, so you can check yourselves right away. And again, as always, if you have questions, let me know on Wednesday. All right. Okay, but I guess on Wednesday we would have another topic. I guess you have started what partial fraction decomposition. So I can answer a couple more problems, or at most 2 problems from section 8.3, then go to partial fraction decomposition next time. All right. So that's it for now. Let's see each other again on Wednesday. Have a good day, everybody, and yeah, bye.